Okay. Welcome, everybody. I'm Matteo Scordino. I'm the co-founder of Elimo Engineering. I will be very quick about ourselves because I have 15 minutes. We are a design agency. We started in 2018. We design custom electronic hardware and embedded software. Most of our devices are revolving around MCUs or sensors or processors with sensors. There's usually a radio involved. We design the whole product from the specification to manufacturing, and because low power is one of our specialties, here we are. So I'll try to be unbiased and look at why, but also why not consider low power design. The obvious why is battery powered devices. We all know them, we all use them. There's the obvious concern of extending the battery life as much as you can. It's not just a technical requirement. It has a strong impact on the user experience. A wearable device that needs to be charged every day is much more likely to end up in a drawer than something that needs to be charged once a week. You have scenarios where having something that doesn't need frequent battery charges or battery replacement is desirable. Typical example is a smoke detector or a sensor that gets installed in a hard-to-reach place and can't have access to mains power. Of course, well, we just had a talk about saving energy, so it's just better for the environment. Even if you have a mains access, you might want to design taking into account how much energy you're drawing. When writing these slides, we spoke about heat dissipation as well, because of course lower power means lower heat dissipation. Usually if you get to the point where you have to worry about heat dissipation, you're already in trouble from the point of designing something low power. But maybe you shouldn't design something with low power taking into account. Sometimes you just can't. You're designing a part of a system that somebody else is designing the rest of, and it's not just part of the build. Or you're forced to use something pre-existing and build on top. As we will see, it's hard to make something low power if it wasn't thought to be to start with. You will have to face compromises with functionality. You might need to sample that key sensor less frequently. You might have to use different components, fewer components, remove certain parts of the system. Sometimes that's just not acceptable, and the use case doesn't fit a low-power approach. It can be acceptable. And then there is the omnipresent concern of cost. A low-power design, as we will see later, will tend to have a higher complexity. That will mean higher non-recurring engineering costs. Your design will cost more. More time, it's going to be probably harder to debug, to troubleshoot. That's some cost that you have to take into account at the beginning. But then you might also end up designing in components that are better for consumption but are more expensive, harder to supply, that are more niche product than something else. It might have a big impact on your design. As usual, there's always a trade-off to be made in engineering. You will have to do a cost-benefit analysis and do it early. We'll see later why. I think this is one of the key takeaways from this. You need to start with a valid expectation. I'll give an example of a typical wearable. You can afford 20 by 30 lithium-ion battery that gives you 150 milliamp hour, more or less, of capacity. Let's say, well, we are Nordic design partners, so sorry, the example is based on a Nordic chip. Let's say you take into account the NRF52832, the core running, just the core, nothing else, will be drawing 4 milliamps on a 3v3 line. At the other side of the spectrum, in system off, that same system on chip will be drawing 300 nanos on the same 3v3. So that gives you a range of 1.5 days to 57 years on that battery. Of course, that's the whole spectrum, right? But it's not a workable range. You can't design based on such a wide number. So it's essential to use the tools that are given to you by manufacturers of devices that are meant for low power design. For example, Nordic as an online power profiler that, given parameters about your system, will give you a reasonable estimate of the average power consumption of that device in that application. Silicon Labs has something similar in integrating in the IDE. They're essential tools to start well with a goal in mind. So what can you do about it? Let's say that you are a master of your own destiny and you can design something to be low power. The key thing is that you can't bolt on low power onto something that was not meant to be. Making something low power is not really a thing unless you redesign it. There can be low-hanging fruit that gives power consumption down a notch. Can help, but it's not the best. And this is a bit counterintuitive in certain respects because people tend to think that early optimization is the root of all evil. In this case, it's not. For low power design, you need to start from the architecture. You will need to do high-level trade-offs, and you will need to decide what to pay in terms of power, where. You will have choices, for example, about do I send this data over the radio and pay the cost of the radio, but don't pay the cost of CPU for processing it locally? Or do I process it locally and transmit 1/100th of the data over the radio? That kind of thing brings us to point 3, which is you need to think across abstraction layers. I'm biased, I'm a firmware designer, but it applies generally. It's not just up to you to make your design low power. You will be working with abstraction layers below you, in my case, hardware design, and above you, cloud or mobile. And there will be decisions that need to be taken across those abstraction layers. Typical example, pins need to go away from a connector because it's too big. You will need to give input to the electronic designers about, well, don't remove that pin, I need it for an interrupt service routine that will help me keep the processor asleep longer. Or similar, as I was saying before, the case of transmitting data. It's expensive. Edge computing, it's a buzzword, but it can help save bandwidth and cloud processing if you look at it from this point of view of backend designers, but it works the other way as well. You can process data locally and avoid sending it over and paying the cost for that. Those decisions, you need to make them at the beginning. If you make them after this stage, you will have to redesign whatever you have created until that point. And this is the nerdy part. What can you actually do? So there are the obvious things. Busy loops are the enemy. Don't keep your processor running if you just need to wait time. The slightly more advanced thing is you have different techniques to get data around. Moving data around is an important part of designing a device, and you could be polling. That means just starting some long-term operation and periodically go back checking, is it done, is it done? Or on a serial line, is there more data, is there more data? Easy, it's the simplest thing you can do, but it wastes power because it keeps waking up the processor. It's more efficient to use IRQs, maybe obvious, but if the processor can sleep and come back to that just when there is new data, that's what you need to do. even better for big amounts of data, DMA, direct memory access. So you have a piece of silicon that moves data around without having to do loads and stores from your CPU. One, I'll say, underappreciated thing is memory-to-memory DMA. If you have a big buffer to move around, it can be more efficient to set up a memory-to-memory DMA transfer and let it go than to do a mem copy. Pros and cons, because DMA, IRQ, they increase complexity of your system and they have a setup cost. So they actually cost power to start. But for bigger things, they pay back. And then there's 3A and 3B because they're conflicting options that you have. You can duty cycle the application as much as you can. You need, well, the CPU is most likely, together with the radio, the most expensive thing to run in your system. Keep it sleeping as much as you can. That would tend to bring you to short bursts of execution. So run something as fast as you can, go back to sleep. Back awake, back to sleep. Back to wake, back awake, back to sleep. It can be good, but all those transitions have a cost themselves. The CPU needs to spin up a crystal again to get out of sleep. That sensor that you turned off needs to be reconfigured when you turn it on again. That kind of thing has a real impact, and for small jobs, it can be an overhead that's bigger than the actual job. In which case, the opposite approach is better, batching functionality that has a high switch cost. In that case, you will be, I don't know, collecting data in a big buffer with DMA and then processing it all in one go. It's more efficient if the cost of bringing everything up and down is high, but it introduces latency. Can you accept that latency? So can you afford to sample data for a minute and then process it? Maybe not. Pros and cons. Libraries. I'll be really quick about this. You need to know what your libraries are doing. There's no point in making an amazing system on your side and then a library is polling every 10 microseconds and you don't realize. Memories. This is a very complex part that I will try to summarize as much as possible. Memories have different power consumptions for different activities. You have flash that's expensive to write, even more expensive to erase. But it's not expensive to read. You have dynamic RAM that is expensive just to keep around because it needs to be refreshed. But then it's as expensive to write as to read. Any external memory, so memory that's not on your CPU, will cause you to go through a memory controller. That's an extra cost. So placing code and data in memory in an effective way can be key. An essential part is using the linker properly. You would like to think the linker will do its job and put things where they should. The job of the linker is to place code and data somewhere where it works. It's not necessarily the most low power choice. And then this is a bit controversial. RTOS as real-time operating systems can save power. True, you can write your handcrafted bare metal system to squeeze out every ounce of energy you can, but will you actually have the time to do all that? Will you mess up at one point? An RTOS takes a lot of that effort out of your hands. It's more important to have a system that's actually low power consumption than something that could theoretically be low power consumption, but will need one more month of work after the deadline. RTOSs have a cost, but they can pay back. Tools. So let's say we want to implement all of this. How do we help? How do we get help? So the first thing is that you can't improve things that you can't measure. Right. You can't improve things that you can't measure. you need to analyze the power consumption, and you need tools for it. Your power supply unit is not accurate enough, is not fast enough. There are tools like the Nordic Power Profiler Kit, good entry-level tool that gives you a high-frequency, nanoamp range reading of what is going on in your system. There are more complex, more advanced, expensive tools like the OT ARC that we use at Elimo that can be programmed, can analyze the behavior of batteries and then reproduce it. You need to compare with what you got with what you expected at the beginning. So that's why I'm referring to tools to compare. What we use at the beginning, the online power profiler, is your goal. Your CPU is staying on all the time, and time I don't have. So it's important to analyze what your CPU is doing with your power, how it's spending your money. There's a free for non-commercial use tool by Sega called System View. It allows you to instrument your code and see what your CPU is doing, either in real time or with data logging. It requires code instrumentation, so it can be an effort to set up. But once it's set up, it will let you see what the CPU is doing, and that's expensive, but also it will give you insight in things that are not the CPU, that are harder to observe, like peripherals that you don't have direct access to, but you can desume what's going on looking at the CPU. Last slide, I promise. The radio. The radio is going to be taking a lot of your power budget. Radios are, a frequent offender of battery drain. It's complex behavior that you have to deal with, especially because radios bring external factors into the picture. All of a sudden, you're burning power not because of what you are doing, but because of what another device is doing, or what a set of devices is doing. That gets very complicated very quickly. A tool like Wireshark, open source, so no cost, is essential. It's a general packet analyzer, but you can use it with a sniffer. Again, Nordic provides firmware for the dev kits to use the dev kit as a sniffer, but other manufacturers do similar things, which means you can have a real-time picture not of just what your radio is doing, but what's happening in the network, and saying that you could optimize that behavior. Or, oh, actually, the problem is not what the radio is doing, but another device is misbehaving. That kind of thing you can't see without this kind of tool unless, I don't know, you're a genius and you can keep 20 devices behavior in your mind. Again, can be a bit of work to set up, but it pays back. And I'm done.
Thank you.
Thank you.
Thank you, Matteo. That was epic. Questions? I'm assuming there's questions. Yes.
Hi. Thanks for the presentation. It's really interesting. My question would be, you say that obviously you need to make sure that you have optimization in mind from the start. But again, say you're a startup. How much do you think this is going to cost? How much time do you think this is going to add in? Most startups do not have time to probably do all the things that you want to do. Like, where's the trade-off between starting or maybe starting at a V2 and making sure your V2 is power optimized?
That's a good point. I would highlight the fact that I said you can't bolt on, you can't add low power unless you redesign. So it's a valid approach. You can't go with a V1 that just shows functionality and runs half an hour. Your marketing team tells you that you need 2 days of battery life, and that will be your V2. So the MVP will just do whatever needs to be done, and that's actually a common approach. It's not crazy at all. You need to budget for it. You are going to do twice the design that you could have done once, and iterating on hardware is more expensive than iterating on software. It's a common startup concept. Move fast, iterate. Iterations are all more expensive in hardware than in software. Can you afford it? It might be better to have that MVP 1 month later and not have to redesign it from scratch. Trade-offs. I know it's not the magic bullet that one would like to hear, but it's the hard reality of fact. There are architectural choices. You are going to have to make them anyways. If you have a device that talks to the cloud, you will have to make architectural choices because your cloud team needs them. You might as well take into account power in that. It might extend that meeting by half an hour and save you 3 weeks.
Thank you. Hardware is hard. Any other questions for Matteo? Ooh, no, go on.
How do you answer the very difficult question from management? How long will the battery last?
Oof. As long as you want. Well, you can have an idea. You can give an idea. You're never going to be able to say it's 6 weeks or 7 weeks at the beginning of the design. But those power profiler tools that I was talking about at the beginning, they are much better than what I could expect, especially when you have a decent idea of usage patterns. That's unfortunately something that's out of the system, hard to take into account, but somehow you need to take into account. There are devices that are almost independent, and those are easier to profile. You can answer that question for management for those devices. A wearable, not so much. Is the user going to turn on the screen every 10 seconds or once every 2 hours? Nobody can answer that question. You can, if you really want to spend time doing that kind of thing, you can have a focus group about typical usage patterns, but then it kind of becomes an academical or just keep the manager happy kind of exercise. I would say you can't give the manager 1.5 days to 57 years as a range, but with profiler tools you can get really close, except for external factors that nobody controls, not even the manager, and that you can explain.
If I may add on to that, for a device that's standalone and
Right.
you know the pattern that it's going to use,
Right.
but your expected battery life is between 3 and 5 years.
Right.
Are there any tools that you can do or processes then to not have to wait 2
Well,
years?
yeah, of course. So extrapolation helps. Look at the shortest period of time you can look at, and of course extrapolate. We've actually done that recently with the OT for a device. It's a building management, like room occupancy. Battery life is expected to be 8 years. We've not designed it 8 years ago. We kind of know because you can profile a prototype. What's important is to have a reliable component selection, because the same functionality can be done with something that burns 50 milli or 50 micro. So essential component selection. You said you know the pattern, so that's out of the way. You have a good shot at giving a reliable estimate. Also, you're talking years. At that point, you need to consider other factors like battery self-discharge, leakage on all kind of random little things. Those you need to measure. If it's that important for you, make the effort of building a prototype and measure a prototype. It's going to give you a month, 6 months plus 6 months minus over 5 years range. It's doable.
I think we'll stop with it's doable. And thank you very much, Matteo.
Thank you.
Thank you.